We're going to look at a number of alkanes, but we're going to start with the simplest one. This has a single carbon with sp3 hybridized orbitals. So we know that carbon must be attached to 4 hydrogens. We draw these bonds as lines in between the letters C and H. That doesn't look right. The molecule isn't flat. There, that's better. Now you can see that the dashed line shows that one of the hydrogens goes behind the screen, whilst the bold line shows that one of the hydrogens is coming towards you. It's a great way to show what is a 3D molecule on a flat 2D surface. We've dropped the letter C, and now when the line changes direction and there's no letter, that must be the location of a carbon. So that's the skeletal form, but we can also describe the molecular formula. We can say the number of carbons and the number of hydrogens. The alkanes fit to a pattern. If there are n number of carbons, then the number of hydrogens is 2 times n plus 2. Let's see if that fits here. So n in this case is 1 for 1 carbon. So the number of hydrogens is 2 times 1 plus 2. It's correct. We do have 4 hydrogens. So we put C, we don't have to write 1 after it, and then H and 4 to indicate 4 hydrogens. But what are we going to name this intriguing molecule? It's an alkane. So how about ane? Yeah, let's call it ane. No, that's not enough. Let's put ane at the end of the name. But what are we going to put at the beginning of the name? It really should tell us that there is 1 carbon. How about meth? Nothing says 1 carbon quite like meth does. I'm going to call this molecule methane. Okay, moving on. We're going to now consider 2 carbons. To our methane, we're going to add a methylene. Whoa, hold on. What is a methylene? A methylene is CH2. So we are adding CH2 to CH4. Let's see what happens. Well, here we have the 3D structure. It's clear we really do need to be thinking in 3D. We can see that 4 of those 6 hydrogens are either going behind the screen or coming towards you. And that's important information. Now, I have warned you before. I think organic chemists are really lazy. So this is far too much work to draw out all these bonds and all these H letters. I don't like writing H letters. So what am I going to do? How about just drawing 1 line? So, just by looking at that 1 line, I say to myself, at each end of the line must be a carbon. And because it's not a double bond or a triple bond in terms of drawing 2 or 3 parallel lines, we must be dealing with a single bond that has sp3 hybridized carbons. Therefore, there must be 3 other hydrogens associated with each carbon. It's tiring work going from that lazy form to what's actually there. But I really encourage you to get used to this lazy format as soon as you can, as you'll be saving yourself a lot of heartache further down the road. Okay, so that is the skeletal form. We'll consider now the molecular formula. So we're talking about adding methylene to methane. So that's to say CH2 to CH4. And if you add them together, you get C2H6. We can see this still fits the CN H2N plus 2 pattern. That's great. But can we break this molecular formula up to show what's going on with each individual carbon? Right now, we are writing C2, and I don't know what each individual carbon's involved in. We can. Here is the condensed form. It's CH3 and CH3. So we are showing what each carbon is bonded to. If we extend that condensed form and draw the bonds in between each atom, we arrive at the Kekule form. Finally, we need a name for this molecule. I did say ane at the end of an alkane, so I don't think we have a lot of choice here. This is going to have to end with ane as well. But what do we put at the beginning? It needs to tell us how many carbons are involved. 2 carbons, so 2 sounds like eth. Please say it does. Thank you. So this is ethane. Now we will add to this a further methylene, CH2. This is what we get. Again, as these alkanes are growing, you can see the 3D complexity is very much there. This time we can see that 6 hydrogens aren't lying in the plane. They're either behind the screen or indeed towards you. So if we're going to be super lazy, how are we going to draw this? Well, we just draw 2 lines. And again, looking at this, you're going to be able to work out where the carbons are and the invisible hydrogens that don't even have bonds drawn to them, that you'll know have 3 on each end and 2 attached to the central carbon. You need to be able to recognize this from a simple lined drawing. That's the skeletal form. Let's move on to the molecular formula. Now we're seeing that we have 3 carbons, and if we use the 2n plus 2 and n equals 3, then the number of hydrogens is 8. What about the condensed form, where we draw each individual carbon and show what atoms are associated with it? Thus, we have CH3, CH2, CH3. Ultimately, we have to provide a name, and I think you're spotting we can't get away without having ane at the end. So it's going to be something ane. The something will tell us that there are 3 carbons, and that's always going to be indicated by the term prop. So a 3-carbon alkane must be called propane. From 3 carbons, we're going to add another methylene to take us out to 4 carbons. Here we can see the 3D structure, and if we're being lazy, we can represent it as 3 lines. You can see the lines are in a zigzag shape, so often it's described as zigzag. Again, we're not drawing the H's, and the C's, we should just be able to look at it and realize they are there. Now we are talking about the molecular formula. Where we have 4 carbons, we must have 10 hydrogens, right? So we're going from there to the condensed form, where we draw each individual carbon and what atoms are involved with that carbon. So here, that is CH3, CH2, CH2, CH3. And a name, it's going to end in ane, and there are 4 carbons. The name must tell us this. Bute achieves this. So we have here butane. If we add another carbon in the form of a methylene, so CH2, We now have 5 carbons to deal with. Here you can see the 3D nature of the molecule. And here we have the skeletal form. Lazy, simplified. No carbons written with a C, no hydrogens written with an H. You need to recognize that they are there. The molecular formula is now C5H12. We have the condensed form where we are seeing CH3, CH2, 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 CH3. And finally, we need to name the molecule. It's going to end in ane because it's an alkane. Pent is how we indicate 5 carbons. So this molecule is pentane. We go from there to add yet another carbon in the form of a methylene CH2. Here we have our 3D depiction of all the hydrogens. This is the skeletal form. It is the simple minimal form. We don't write carbons and we don't put any hydrogens in here. The molecular formula is going to be C6H14. And now we have the condensed form. CH3, CH2, 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 and CH3. The name is going to end in ane with hex indicating 6 carbons. So we have here hexane. From there, well, yes, another carbon is added as a methylene CH2 group. So here we have the 3D form. Here we have the simple structure, not drawing carbons or hydrogens. The molecular formula is going to be C7H16. And for the condensed form, we have CH3, CH2, 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 CH3. The name will end in ane, with hept telling you that there are 7 carbons. This molecule is heptane. Going from there, 1 carbon more, we are looking at this structure. Here is the simplified version. The molecular formula now is C8H18. The condensed form is CH3, CH2, 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 CH3. The name is going to end in ane with oct, telling us that there are 8 carbons. So this is octane. Okay, going from 8 to 9, we're adding another carbon as a methylene. So 2 hydrogens are coming with it. Here we have the 3D structure. And here's the simplified skeletal form. The molecular formula is now C9H20. Here we have the condensed form. I'm not going to read it all out now. It's getting rather long. But what do we call it? Well, it's going to end in ane, and we need to tell people that there are 9 carbons, so we say non. So here we have non-ane. Obviously, we could go on and on and on and on. But finally, in the sequence for this discussion, we will stop at 10. From 9, we add 1 more carbon. We added it as a methylene, CH2. Here is the 3D structure of the 10 carbon molecule and the simplified form. And next we see the molecular formula of C10H22 and the condensed form. But what are we calling it? It has to end in ane, but what tells us about the 10 carbons? That would be dec. Thus, here we have decane. So far, we've been looking at a long chain with 2 ends. But what would happen if we attached or bonded one end to the other? Well, then you would have a ring. And there are a variety of ring alkanes we can make. But we don't normally call them ring alkanes. So, what do we call them? We have ane telling us it's an alkane, and in the middle we still need to know how many carbons are present. At the beginning we are going to use the term cyclo. That tells us it's a ring. So here on the left we have cyclopropane with 3 carbons and 6 hydrogens. Now hold on. Shouldn't it be 3 carbons and 8 hydrogens? Not 6 to fit with the rather wonderful formula of 2n plus 2. Well, the 2n plus 2 was only applicable to the chain systems. For the ring systems, where there are n carbons, there are just 2n hydrogens. We've lost the plus 2, as those 2 hydrogens have been replaced by the bond joining the chain up into a ring. After cyclopropane in the same series, we have cyclobutane, cyclopentane, cyclohexane, cycloheptane, and cyclooctane. Again, we could continue on up, but for brevity we will stop there. Note that all the molecules fit the CnH2n formula, and that the variation is occurring in the middle section of the name as the number of carbons present changes.